Okay, today we're going to look at the concept of standing waves. Very important concept in physics. It's used everywhere. It's used in medicine. It's used in engineering. It's used in physics, chemistry, bio, everywhere. It's a super important concept. It's used in sports as well. So it's something that you really need to learn about and to understand. And it's not hard to understand once you understand the idea of interference. So we're going to do a short lesson on this, and then there's a few other instructional videos posted on the website that I would suggest that you watch. They have a very, very good description and understand explanation of this concept. Okay, so what is a standing wave? It's not a person standing up waving. First joke ever. But standing waves are created when a wave reflects back on itself with the same frequency, wavelength, and speed. Okay, so what does that mean? So first of all, I would highlight that key point, and we're going to add to that in just 1 second. So standing waves are created when a wave reflects back on itself with the same frequency, wavelength, and speed. Now, what we're essentially talking about here is periodic waves. Okay, so periodic waves are waves when you set them in motion, right? I'll speed this up just a little. Okay. Now I'm going to unclick all of these. So, oh, sorry, I have to show the instant wave. There we go. Okay, so as the wave comes in, you can see the wave coming in, and you can see that it's a periodic wave. So there's a crest, a trough, crest. So now you can't see that the waves are actually just going up and down, okay? Let me see if I click resultant wave. What does it look like? All right, so there we go. Hit resume. Okay, so you can see that that's the resultant wave. So there's just one wave coming in. It's got a very specific wavelength measured from crest to crest, or one period, or trough to trough, one period, or from here to there, which is one period. And that's so the distance from there to there is one wavelength. Now you can see the wave is moving. So the particles are going up and down in the wave, but it makes it look like the wave is moving. But the particles, remember, they're transverse going up and down. Now here's the key. We've got a fixed end here. I'm going to ask you, when this wave hits the end, what happens to the wave? Now a little N popped up. We'll talk about that in a second. Right here, when the wave is incident on a hard boundary, so it goes from a slow boundary here to a fixed boundary, the wave will invert and reflect. Okay, so if I hit resume, you'll see nothing happens. Okay, now there is something weird happening with this resultant wave, but we'll talk about that in a second. So basically the incident wave just keeps going through. Okay, so now what we'll do is I'm going to reset this, start it, and I'm going to show you the reflected wave as well. Okay, that's the resultant wave. That's what that's what the overall wave effect will be. Now remember, resultant wave is really just a superposition of any waves that are interacting. So, if they're crest and crest, so right away you should start thinking about the word interference. Okay, now I'm going to take that off, and then we're going to start to see what happens. There's going to be a reflected wave. Boom, there's a reflected wave. Okay, pause. So as the incident wave hits, it inverts and reflects and moves backwards. But now you're going to notice something. There is a wave here and a wave here. They are equal in size, but opposite in direction. So the principle of superposition tells us that if there's a positive amount here and a negative amount here and they're the same, you're going to get destructive interference, and there should be a flat line here. Let's look at the resultant wave. There is a flat line. Okay, let's move it. Now watch this. Okay, now the incident wave is still coming. The reflected wave is moving back, and the reflected wave is in the same direction in magnitude as the incident wave. What's going to happen? Well, these two are going to add together and should give a really big wave. And look at that. How about right there? If you said, oh yeah, well look, there's same opposite, it should be a flat line. And there's a resultant. What do you get here? Two crests meet, big, two troughs meet, big trough. Correct. Notice there's an N, an A, an N, an A, an N. Let's continue it. gone, N, A, N, A, N. Okay, and you're like, okay, so what's happening? So you can see they're interfering with one another. And I think you get the point at this point. Okay. Now, what you're going to notice here is that what about that point? Well, that's an awkward point because you got some overlapping, some not. So you're going to see it's still there, but it's starting to look a little bit different. I'll try and go right there. You'll see it's like these things are still there because they're still adding at those key points and destructing at those other points. Okay. So what does the overall result look like of these waves? So it's the incident waves are interacting with the reflected wave. That's the most important part. The incident waves are reflecting and interacting or interfering with their reflected waves at a very specific period and frequency. Well, let's see what this looks like. This results in what's known as a standing wave. Now, to show this with slinkies and stuff in school is like really cool. And if you watch some of the extra videos, they'll show some examples of that. So if I get rid of the incident wave and the reflected wave, that is what you actually see. That is the result of sending a periodic wave into a medium, have it reflect off a boundary, and come back. Is this really cool oscillating standing wave? And they call it a standing wave because it looks like the wave is just oscillating up and down at that very specific point. Okay. Now, and it's not moving, but in reality, it's the superposition of a incident and reflected wave. Okay. So really that's what's happening. But you don't see that. You always, just like in the water waves, there's millions of waves interacting to give you the resultant waves. Here, you just have these two incident that are giving you the resultant wave. Now, I'm going to pause it. Okay. Now, what you'll notice is that there's N's and A's. And here, from an N to an N, from an N here to an N there is one wavelength. From an A here from an N here to the second N is one wavelength. So from one N to one N is a half a wavelength. From this A here, past that A to that A is one wavelength. So there seems to be two N's in between for one wavelength and two A's. So what are these N's and A's? Well, let's talk about it and take a look. What do you notice at this point where there's an N? The wave is stationary. It actually doesn't move. The particles there are stuck. They just sit there. And that is called a node. N-O-D-E, a node. And the point where there's maximum oscillation, or the A, is called an antinode. So node is an area where no matter what's happening, there is always destructive interference 100%. Wherever there's an A, there's constructive interference. And then in between these different areas, there is a mixture of constructive and destructive interference. So a node is an area where there's completely destructive interference. There's no motion of the particles up and down. And an antinode is where there's maximum displacement of the particles, called an antinode. Okay, so let's consolidate this into this next part, and then we'll move on to some examples of this for you. Okay, so the key points are for standing waves. The key point is the incident waves reflect back and interfere with each other. I don't know what that E's there. With each other. Both, you get destructive and constructive interference happening. So it makes it look like the particle, or makes it look like the wave is just stationary and going up and down and up and down. Anybody that plays an instrument, guitars, flutes, what doesn't matter, any instrument, stringed instrument, musical instrument with a wind instrument, All of it's the same. They're all just standing waves. What you're doing is setting up standing waves on a string or in an air column, and it produces resonance or standing waves, which are amplified tones and notes. And that's what you're doing. And if you miss one, if you have the wrong frequency or the wrong tension in the rope, you don't get resonance properly. You don't get a proper standing wave set up, and you don't get the right note. And it is entirely physics. There's nothing else to it at that point. All right, except for learning how to play it and be skilled at it. But that's a whole different thing. From the superposition principle, remember that word, the destructive and constructive regions of interference can be predicted. Points of completely destructive interference are called nodes, right? And the key was that the N is there. And areas of completely constructive interference are called antinodes. A. All right, let's say you have a standing wave. Now we're going to start talking about things like first harmonic, third harmonic, second harmonic, fourth, fifth, sixth harmonic, right? So a harmonic is one of these vibrational modes. Now, what you're going to notice from the applet, I want to show you something important. When you have a fixed end, notice here, because the end is fixed, there's no chance you could ever have an antinode here. Why would you? So it's like it's attached to the wall. So why would it ever have a maximum amplitude of an antinode? So there's always an antinode. Over here, there's a fixed end, right? And of course, how are you going to get one if there is you can't allow it to vibrate. So there's a node there. So no matter what in these instances, if you have a fixed end or fixed at both ends, you always have an antinode. Sorry, a node. So it says here, fixed at both ends. All right, so if it's fixed at both ends, then what you end up with is simply a node at this point, a node here, and a node here. Now it's called the third harmonic or the third vibrational moment because if it starts at a node, it has to end at a node. So that would be the first, the second, and the third. So how you draw these is a little tricky. Some people are really good at it, some people just really are not. So I kind of like sometimes I'm good, sometimes not. So I do this to show the first sort of vibration, but now to show that it's a standing wave, and that would be an antinode, that'd be an antinode. Now to show it's a standing wave, what I do is I do a dashed line underneath to show that it's going to be oscillating up and down between those 2 points. So this is the oscillation is happening here, right? It's going up and down, 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 up and down. And the waves, remember that it's actually just a wave that's moving this way, reflecting, and then interfering with itself and producing this resultant wave. Now, you can see that the nodes are where you're getting it's completely destructive interference, okay? And it shows here an arrow from node to node. Well, if you are thinking about this, and we've talked about it just in that last little bit, if you get a highlighter and you go, okay, well, from there to there, up to there, that's considered one wavelength, okay? It's where the oscillation starts to repeat itself, and it's, that's the one wavelength section. So from node to node, there is actually a half of a wavelength there. You don't like fractions, but you have to get comfortable with fractions. It's so important. It's half a wavelength. So the distance between nodes is lambda over 2, or 0.5 lambda. Okay. Well, how about antinodes? Well, from an antinode, let's say here, so that's an antinode. So from an antinode here, it's also down here. It doesn't matter. You can label it. Some people just put a line across the equilibrium position here, and they'll say node, antinode, node, antinode, node, antinode, node. Right? I put it up there, but it's at the top or bottom. It's just at this point. Okay. And then there's a mixture of constructive and destructive interference happening there. So from antinode to, so if you start up here, the next antinode is there. Well, from antinode to antinode is only there to there. So that's exactly half a wavelength as well. Okay. What I would suggest is that we're going to look more into this in just a minute on the next activity. We're standing waves student notes, and we're going to talk about the different harmonics and what it looks like. And there's also 2 other instructional videos on the website that you should watch that really explain the concept of standing waves and the next part that we're looking at. Okay, we'll move on to that now.